In this video, I will talk about the signed area. Before I do this, though, I would like to introduce a little online tool which can help us to visualize the Riemann sums. So here, first of all, I show you again the definition of a definite integral of f from a to b, which we write as integral a to b, f of x dx. It's a limit for n goes to infinity, and then the sum of f of x I star delta x, where delta x is the size of the subintervals and then xi star are the sample points within the subintervals. And then we had seen the right point rule, the left point rule, the midpoint rule, all this beautiful stuff. So here's a link for mathworldwolfram.com, Riemann sum HTML. And I like to look at the example integral from 0 to 1 x times 1 minus x squared dx. So let's open this up. So here it is. And you see already I plotted the function right here. And in this setup I have used the midpoint rule, indicating here using 10 subintervals or 10 rectangles. And then the integral goes from 0 to 1, and the function is here, x 1 minus x squared. Okay, and then we get the estimated area, which is the sum of the area of the rectangles, to be 0.25125. The actual area is 0.25. So you see, using 10 rectangles and the midpoint rule, we are actually really close to the actual area. Now we can play with the rules here on this pointer, so we can use the left point rule, for example, replot. Okay, so then you see the rectangles are always touching on the left corner. Okay, and here they're a little bit below the curve, and here they're a little bit above the curve, but it's still always the left corner point. And so the estimated area is 0.2475. A little bit smaller, but still pretty good. And using the right point rule, replot. Yeah, then we touch the curve on the right point of these intervals. Sometimes we are a bit above, sometimes we are a bit below. And we get an area of 0.2475. Oh, the same number as for the left point rule. Let's go back to the midpoint rule, because this is often the best approximation. And now we can improve the approximation by making it finer and finer. Okay, so maybe let's use 100 points. Replot. Oh, you see, these are now 100 subintervals. It follows the area super closely. And we get 0.250012. A very, very good approximation. So, but now, what happens if I change the boundary of integration? So here I integrate from 0 to 1. Next I would like to integrate from 1 to 2. And then something very interesting happens. So here I write down the integral from 1 to 2. But if x is between 1 and 2, then this term here is actually negative. So meaning the whole function is negative. So what if f is negative? Let's look at the definition, right? The integral is defined by the Riemann sum. And so f is this guy here. So we are evaluating f at these sample points. Now if f here is negative all the time, then the whole sum is negative, right? So then the Riemann sum is negative. So what does this mean? Does this mean we have a negative area? There's no sense in a negative area. Okay, let's use our Wolfram Alpha app and try this out. The same function, but now I change the boundary. So now I go from 1 to 2. Use 10 rectangles, midpoint rule, replot. Aha! So now the function is shown from 1 to 2, and in this interval the function is actually negative. So now I build rectangles, but they all go down. Okay? Because the function is negative. And see what we get for the area. We get the area of minus 2.24625, where the actual area is minus 2.25. Now this is rather interesting, isn't it? We get a negative area out of this. Or in other words, you could say, the negative of the integral is the area. Okay? So the negative of the integral is the area, and that's why we call it a signed area, because the area seems to have a sign. So what happens if we use 1.5 here? because this is a number I need later. Now this goes to 1.5 and the area is minus 0.39. Here you see the full function. F of x is x times 1 minus x squared. And you see it has positive and negative parts. And the corresponding areas between the curve and the x-axis will then be equipped with a sign. So for example, here we first integrated from 0 to 1, so this area. And so the signed area here was actually plus. It was 0.25. And then we integrated from 1 to 1.5, so maybe here. But now this got a negative sign. So here we say the signed area is minus 0.39. And then we can continue in the other bits. So if we integrate, let's say, from minus 1 to 0, we would get a minus sign and have a signed area here. And here the area between the x-axis and the curve would be positive. So that's why we call this integral from a to b for any function, f of x dx, is the signed area. If the function is positive, it is really the area under the curve, but if the function is negative, it is the area between the x-axis and the function. So let's compute one particular integral just for the fun of it. And I need a little bit of space here. So I like to compute the integral from minus 1.5 to 1.5 of this function f of x dx. So it is the integral from here all the way to here. Okay, so now the integral will collect all the areas which happen between the curve and the x-axis, but also obey the right sign. So use a plus sign here, a minus sign here, a plus sign here, and a minus sign here. The first we do is we divide it into subintervals. So we can write this as the integral from minus 1.5 to minus 1 f of x dx plus the integral from minus 1 to 0 f of x dx plus the integral from 0 to 1 f of x dx, and then plus the integral from 1 to 1.5 f of x dx. So let's call this area now A1, this area A2, this will be A3, and this will be A4. And we computed A3 and A4 already. Now from the graph, and also from the symmetry maybe, you can see that A2 and A3, they're actually the same size. So then we get this would be A1 minus the size of A2 plus A3 minus A4. By geometry, we find that actually A2 and A3 are the same size, as are A1 and A4. But you subtract them in the above formula. So meaning the integral, which I had here, minus 1.5 f of x dx, is actually equal to 0. So that's really funny. So the function is not 0, obviously, but the integral can actually happen to be 0. And this happens if the pieces of the area balance exactly. So those pieces of the area above the axis and those which are below the axis, they balance, and so together this integral is actually 0. Let me summarize. So the integral of a to b f of x df, where f is an arbitrary function, this is really the signed area under the curve. And now I put under in quotation marks because, well, yeah, here we are under the curve, right? But here we are actually over the curve. So it's really the area between the curve and the x-axis. A way to understand this is that the integral from a to b f of x dx are those areas where f is positive, so maybe this one and this one, minus those areas where f is negative.